You are viewing one of 10 modules developed through a project funded by Geoscience BC focused on direct-use geothermal resources in British Columbia. This follow-up project was carried out between August and December 2016. The project was executed by Tuyaterra Geocorp. These modules were developed from the Direct-Use Geothermal Resources Roadmap published by Geoscience BC in June 2016. They incorporate additional educational material that were developed as part of the current follow-up project. The voices you will hear narrating the module are myself, Catherine Hickson, and my colleague, Juliana Proenza.
Welcome back, everybody. We are currently on Module 9, and we'll be going through a few case studies on how GeoExchange and direct use can be developed in the province. For this module, we'll mostly be going through the bottom half of the slide, which is the capabilities of GeoExchange for direct use projects. Some of these projects cover applications such as residential heating, aquaculture, and greenhouse heating. But I did just want to point out that direct use is used in BC currently. There are hot spring resorts throughout the province, and there are currently 3 projects that are in development for direct use and or power, and these are Slowcat Creek, which is currently being evaluated by the Douglas Zaza First Nation. They are looking at expanding their site at Slowcat Creek and received funding from the BC Rural Dividend Fund to do that. And then we've also got Borealis Geopower working with Valemount at the Canoe Reach project and working with Kitselas at the Lake Hells Lake area, which are both known geothermal areas, and looking at developing those for potential geopark business customers for heating purposes and also power production. You can find out more information about the Canoe Reach and Lake Hells Lake project on the Borealis Geopower, so you can go ahead and Google that if you're interested in finding out more. So let's go through some of the case studies for how GeoExchange and direct use work together for providing heat for different end-use applications and provide the opportunity to decrease greenhouse gas emissions. I know we've gone through some of these details in previous modules when we were going through what GeoExchange is, but just as a reminder, basically it's the simplest geothermal system. It's referred to as GeoExchange by Canada GeoExchange Coalition, but it's also known as ground source heat pumps, geothermal heat pumps, earth coupled systems, and earth energy systems. Essentially, it is a ubiquitous energy source and it can be used for cooling and heating throughout the year. So depending on the location, at depths of 5 to 10 meters, a constant temperature is maintained. And Natural Resources Canada and the US EPA have both recognized that GeoExchange is the most energy efficient, environmentally clean, and cost-effective space heating and cooling system available on the market. So I've included this graph here to really showcase that you're essentially using the ground as a heat source for heat in the winter, and then you're using the ground as a heat sink in the summer to remove heat from your home and put it into the ground. So you're using the ground as part of a closed system with your home or whatever end-use application you're using. For the most part, usually it's a closed system. You're using the constant temperature in the ground as a heat source for heating and hot water. But once you've got a GeoExchange system in place, that this isn't necessarily something that's useful if you're only using it for one residence, but if you've got a district heating system that's using GeoExchange, the efficiency of the system can really be increased because you've essentially interconnected different types of buildings that have different heating and cooling loads, and you're on top of the fact that you are using the ground as an energy source, you're also using all of the buildings that are connected within that system as a heat source or sink. So you're moving heat essentially from one area that doesn't need it and putting it to another area that may, and then you're only drawing from the ground when you need it. So you're really maximizing the efficiency of the system if you can use the different characteristics of different types of buildings that you've connected together. So for example, community ice rinks are always rejecting heat in order to maintain a cool environment. So that heat is generally wasted, but if you've got a community ice rink included in a district energy system, you've got that heat, you've got the community ice rink essentially as a heat source where you're always removing heat from there and having it to move somewhere else. So electricity is required to run the heat pump systems, but the fuel is essentially free, and that's the main point here. So heat pumps essentially, you're probably thinking, how do I use the ground temperature at 10 degrees to help me take a warm or hot shower that may need, like, let's say 40 degrees for that. So what happens is that heat pumps are essentially assisting a geothermal system by raising the intake temperature to more desirable levels of, say, 40 to 60 or 70 degrees Celsius. And how it does that is that the fluid that's actually providing the heat is a secondary fluid. It's not water that you're actually extracting from the ground. You're using the ground as the heat source, and then you're moving that heat to another fluid, which is the working fluid, and it's usually a refrigerant. And the refrigerant has favorable thermal properties where it changes from a liquid to a gas at that lower temperature. So you do need the electrical input at the compressor, and so what the compressor does is increases the pressure and as a result the temperature of that working fluid to the point where you can pass on the heat of that working fluid to space or hot water in your home or whatever application you're using the heat for. So as I've mentioned, these types of systems are being used in various hybrid technologies that incorporate the heat from wastewater or ocean water, or hybrid systems with solar, hydro, and other alternative technologies. So one of the case studies that we'll be looking at is the Alexandria District Energy System, which is in Richmond, BC, here in the Lower Mainland. It has been developed since 2010-2011. The first phase of the district renewable energy system was to incorporate the first phase of the building, and they essentially were using a ground source heat pump technology to extract heat from the ground via a network of vertical pipe loops. And so the system was designed to handle the capacity of expansion as the neighborhood develops and as demands require more supply. So phase 3 was completed in December 2015 and now provides energy to 5 residential buildings that equal almost 1,200 units and 1 institutional building. And then phase 4, which was scheduled to be completed in fall of 2016, it will expand the system to service large commercial development in the neighborhood as well. This system provides space heating, cooling, and domestic hot water. It provides a safe, clean, reliable external energy source which reduces greenhouse gas emissions. What the system was basically composed of was 385 boreholes at 76 meters deep, and it was drilled beneath a city greenway corridor. And so how the system works is that heat pump units in each building elevate the water temperatures for heating, or it rejects heat into the system for cooling. And as I mentioned, the system was designed to allow connection of additional buildings into the system, and there is a 1 megawatt condensing gas-fired boiler used as a backup energy source, and is there also to provide supplemental peak load if required. So we'll be including a short video that highlights the project, and it's about 3 minutes. Enjoy that video, and I will meet you on the other side.
The City of Richmond is a proven leader in reducing reliance on non-renewable sources of energy. On March 31st, 2011, in partnership with Oris Geoenergy Limited, Richmond broke ground on the innovative Alexandria District Energy Utility.
Today we celebrate the launch of construction for our first city-owned district energy utility.
The Alexandria District Energy Utility uses GeoExchange technology to heat and cool new residential and commercial buildings in the Alexandria neighborhood. Drilling deep into the soil and installing a pipe system allows this technology to tap into ground source energy. Here's how it works. Water is pumped through this network of pipes and picks up the ambient heat from the earth. The heated water is then distributed to the heat exchangers located within the customer buildings. In cooling mode, the energy flow is reversed and heat is pumped back into the ground.
So ladies and gentlemen, the Energy Center, which is right behind me, it forms part of our $4.8 million investment in new infrastructure. The system is mostly hidden from view. It represents a giant step for our city as we provide clean, affordable energy. 1, 2, 3. We're open. We're open.
The Alexandria District Energy Utility will substantially reduce greenhouse gas emissions. In the first two phases, the Alexandria District Energy Utility will service the Mayfair and Remy buildings that house more than 500 new residences and a daycare. The utility is wholly owned by the City of Richmond, and with revenue from the customer base, it is financially self-supporting. The Alexandria District Energy Utility is adaptable to future technologies and other sustainable energy sources, such as sewer heat recovery and solar. The Alexandria District Energy Utility. Clean, efficient energy for now and the future.
Okay, so we've gone through a more dense development in Richmond, BC, and now we are looking at more of a sprawled out neighborhood. New housing development project that was developed in Gibsons BC on the Sunshine Coast. So for that project, there was a desire by the community to minimize greenhouse gas emissions as much as possible, and they specifically want to promote the use of geothermal systems. And similarly to the Alexandria system, the GeoExchange system at Gibsons took into account that as the development will grow, additional commercial space will be added to the system and will help balance the heating and cooling loads. So again, that's really speaking to the versatility of GeoExchange systems, where heat rejected from cooling commercial buildings will replace the heat that's extracted by homes. And these interconnections between buildings really reduce the size and the cost of the GeoExchange systems, are a really integral part of the system. So a few other characteristics of the Gibsons District Energy Utility was that the storm sewers servicing the development required rebuilding. And so when they were going to do that, they also decided to provide a connection to the ocean that was installed at the same time. And what that does is it helps to moderate the temperature that's used to ensure that the GeoExchange system can be maintained at efficient operating temperatures. So for this development, the lot sizes were fairly small, but there were approximately 150 homes in the initial stage, and there is the potential for an additional 250 to 300 homes as the development progresses. And they've left that potential for those connections, and they've already built them into the system already. So one of the things that they originally looked at was doing a vertical system and drilling into the aquifer that was beneath the proposed development. But the town of Gibsons did not want to do that because of the potential for contamination to their only water supply. And so parks and greenways were essentially used as the necessary space to install the horizontal ground loop configuration. So initially they thought that horizontal geoexchange would not be possible, but they were able to evaluate the areas nearby and able to make use of the parks and greenways that were part of the development in order to supply the needed area for horizontal ground loop configuration. So connections to a second pump house and commercial development will provide load diversity as the development moved forward and facilitate energy transfer between buildings. And that's just highlighted here with the empty future ground module connections there. So it won an award in 2009 and was the first municipally owned system of its kind at the time. As I mentioned, the first phase was 133 homes, duplexes and cluster homes. I've included here a link for a webinar that discusses the system in a little bit more detail that was hosted by the Green Municipal Fund. And I just wanted to highlight that there's different ways of financing these types of systems. And so in the case of Richmond, the developer financed the system and then is providing the heat to the homes and charging a monthly fee for that, and that's how they are making their revenue. Whereas in this case, the majority of the cost was actually shared by the developer and the town. And the majority of that was by the town. So it is a municipally owned system, and then each homeowner was required to pay a certain amount of money per home in order to connect to the system. So just some of the characteristics of the resulting system was that estimated carbon emissions were reduced by 1,400 tons annually, and investment in the system was expected to have an internal rate of return of approximately 15 to 20%. And so what that has really done is that this forward thinking of allowing connections in the future and demonstrated concern for the environment has attracted people and businesses to the community and really helped to drive economic development in the community. So moving on to a slightly different example where geoexchange is being used for aquaculture. We've got the Chapman Creek Hatchery that's run by the Sunshine Coast Salmonid Enhancement Society that is just to the northwest of Gibsons in Seashelt. The hatchery is dedicated to sustaining and building salmon and trout stocks in local waterways and facilitating public education regarding salmonid habitat and life cycles. And so they were looking at replacing their heating system with a geoexchange system. And so there was a feasibility done where a geothermal heating system for the facility was designed as a hybrid system to include the design for a 5 kilowatt micro hydropower system as well, that essentially provided the power input required by the geothermal system. And so it's a self-sustaining system. The micro hydropower is based on using the exiting water supply pipeline as penstock to utilize the wasted head and flow from the hatchery without compromising the required flow for the hatchery's fish tanks. So basically water that is already flowing through the hatchery tanks drives 3 microturbines. And then an open loop geothermal system was designed based on the local hydrology to replace the existing electrical heating of the facility. And so the resulting system saves up to 75% on power consumption. It reduces the carbon footprint of the facility and the operating costs. And as I mentioned, the hydro generation is sufficient to run the geothermal heat pumps, making the facility 100% energy efficient, and the excess power is sold and generates a revenue stream for the hatchery. And the last example that I've got here is a geoexchange system that has the potential to provide heating for a fairly large floricultural facility in Chilliwack. There was a comprehensive feasibility study and design completed for the development of a 4 megawatt geothermal heat pump system, and the project was awarded just over $1 million in government funds towards implementation. What that project would do is it would reduce 70% of greenhouse gas emissions of the facility and improve the energy economics and sustainability of the greenhouse. These examples are really provided to showcase that there are all these areas in BC that have higher heat flows and could provide direct use capabilities of higher temperatures for industrial processes and other uses, but you really don't need those thermally anomalous areas to develop geothermal projects. We've got here a few different examples that showcases how you could use just engineering and ingenuity to provide heat to different applications using the heat right below your feet in the ground.